Hey everyone, welcome to our inaugural Haskell Study Group. I'm Ram Vedam with Atlanta Functional Programming. The Haskell Study Group was a new initiative being created by the Atlanta Functional Programming Meetup, has an effort to explore the Haskell programming language and its ecosystem. Its goals are to not only present the language as a whole, but to provide some common tools. Um, I hear somebody in the feedback. Could someone put them? Um, the it the goals of the meetup is to provide kind of an environment to not only teach and provide a way to learn the Haskell programming language, but to provide common tools that are used for day-to-day development and an understanding of some of the available patterns and ways of designing and engineering Haskell software. We're going to be exploring a lot of that. To start off, we are actually going to be presenting today a talk on the Lambda calculus, which is kind of the basis for actually learning the programming language. It's very simple in its concept, very complex, as you will soon see. Our presenter is my fellow co-organizer of the Atlanta Functional Programming Meetup, Judd Taylor. I won't take too much time than I did already. Just one note for folks who are watching our live stream. Please post your questions on the live stream, and I am moderating those questions. So if there's a particular question that we need to interrupt the speaker on, I'll do so at the appropriate time. Thanks. Without further ado, Judd, take it away.
Okay, thank you, Ram. And one other minor note. Apparently we measured last week, and there's apparently a 10-second difference between Google Hangouts, which is faster, and YouTube, which is slower. So take that into consideration depending upon which medium you're watching this through. Okay, so for the presentation, this again is just an introduction. Well, this is an introduction to the Lambda calculus. And I pose the question, why? Which then, really, why not? And this might mean something by the end of this presentation. Those two expressions are the Y Combinator and then the not encoding. Go back to this. Okay, what is the Lambda calculus? Lambda calculus is a formal system in mathematical logic for expressing the idea of computation, which was of big concern early in the 20th century. It captures and represents the ideas of functions, parameters, values to go in through those parameters, and then calculation via a process that's called application. And Lambda calculus was devised by Alonzo Church, who I believe was at Princeton at the time, in 1936. And Lambda calculus is very deeply and solidly embedded in some great languages like Lisp and Haskell, and also some other languages are increasingly having anonymous functions or lambdas incorporated. Okay, why should you care? Well, first, it's pretty cool. It's interesting in itself. It relates to computer programming and some other subdomains of philosophy. And it's, again, central to functional programming languages like ML, Haskell, and Lisp. And then understanding a Lambda calculus will probably help you make their performance for you better. Okay, there are other models of computation, right? And then others, kind of well-known ones, are the Turing machine, invented by Alan Turing, mu recursive functions, finite state machines, and push-down automata. So finite state machines and push-down automata can be shown to not be as powerful as Turing machines. Turing machines, in turn, are equivalent to expressions in Lambda calculus. So the early history is, in 1928, David Hilbert posed the Entscheidungsproblem, the decision problem, and the question is there one or more algorithms that can determine, given an arbitrary statement of first-order logic, whether that statement is true or false? Okay, so we don't know exactly what proposition will be posed to be evaluated as true or false. So we want a general deciding algorithm. And so that was his question, can this be done? So in 36, Alonzo Church wrote a paper on that problem using his newly invented Lambda calculus, proving that it cannot exist. And then 2 months later, same year, and independently and not knowing anything about each other, Alan Turing wrote a paper using his concept of the Turing machine and reached exactly the same conclusion. And then within the next few years, the Lambda calculus, the Turing machine, and mu recursive functions were shown to be equivalent. So any problem that could be posed in one could be transcoded into an application in the other. So pretty nifty. But yeah, Turing ended up having to go study under Church at Princeton rather than the other way around. And these are the guys. So that's David Hilbert on the left, that's Church in the middle, and Alan Turing on the right. Turing, of course, is famous for, he's going to be on the 50-pound note, I heard. And he worked at Bletchley during World War II, breaking the Enigma machine, or rebuilding the Enigma machine. So quite a guy. So what's a calculus? It's it is, in general, it's a system of some symbols, some rules to construct valid expressions using those symbols, and perhaps some punctuation, and then rules to operate on symbols to generate new expressions. And basically, we have the goal of simplifying some complicated expression or problem and coming up with a simpler expression or a solution. And that's what we're going to do. So what is an operator? An operator is basically something, an abstract thing that acts on other abstract things, which are inputs, parameters, values, and then produces another abstract thing, which is an output or a result or an evaluation. And there doesn't need to be any concept of types. And there is no, if you have a concept of types, you don't need to have the result match the input types. Okay, so here's some examples. The plus sign is an operator that takes one or more numbers, sums them up, and returns a number. All right, so that's input types and output types are the same. And is an operator that takes two Boolean values, true or false, and then returns one Boolean value. So again, the types are the same. Greater than takes two things and returns a Boolean based on whether the value that's on the left is larger somehow than the value on the right. And so in general, the concept could be used for comparing numbers, but it could also be used for comparing strings according to some like alphabetical ordering or something like that. And so Lambda, which is the operator we're going to talk to about today, it takes a parameter symbol, an expression, and maybe some values, and then returns a transformation of the expression, right?
Can I just ask one question on this slide? On operators, could you put, yeah, so some of these operators could also take an expression that returns a value, right? So like, for example, and could take in an expression like, say, x greater than 5 or something, and as long as it returns a Boolean value, it can still be, the evaluation can still go through, right?
Yes, that's a great point. Yes, it must take as its values either kind of concrete values or expressions that in turn evaluate to something that it can use. So great point, and I will certainly add that.
Okay, thanks.
Sure, thank you. Okay, so what is Lambda? Again, it's an operator it operates on three things. The first is the parameter symbol, which you'll see will be immediately to its right, and then some expression, which will be, it's called the body, and it is basically the body of a function to operate on, and then perhaps a value list of inputs to take in via parameters and then use in the evaluation of the expression. Hold on a second, I'm about to cough. Okay. So then the result of applying the values passed in via parameters to the body is another expression which could contain one or more lambda operator parameter pairs, meaning there's more work to be done by taking in values via parameters. Certainly will be a smaller value list because we have basically one input value, and then it should generate an expression that might in turn be able to be further evaluated. And so we'll walk through these things. Okay, so here is a grammar of Lambda expressions. So an expression is going to be something that is either an identity, and that is a symbol like a letter A or the letter X or something, or a constant. So we can use Lambda calculus and just pass in actually the number 2 if we feel like it. Or this next one is called an abstraction. And this is an expression that consists of the symbol lambda followed by an identity, which might be the letter X or some variable named foo or something like that, and then a period, and then an expression, right? So now if you're following, you'll see that expression, now that's a recursive instance of expression, right? So, and then an expression could actually be the concatenation of 2 and therefore more expressions, or it can be divided off using parentheses to show precedence of calculation. So the identity symbols can be anything reasonable. So any letter, probably maybe don't want to use numbers, except as subscripts or something. And then there is some punctuation, left paren, right paren, lambda, dot, and often the square brackets are used to help us humans during the evaluation of these things. And then associativity in lambda calculus is to the left, meaning that ABC is equivalent to left paren AB, right paren C, not A, left paren B, C, right? So if we're going to evaluate from inside parentheses toward outward, AB would be evaluated before the result of that would be evaluated with respect to C. And the opposite would be in the case of A, left paren, B, C, right paren.
So in that case, you're saying that C is evaluated first, right? It's a right to left evaluation.
I would put it simultaneously. I would say that AB is somehow evaluated simultaneously with recognizing the value of C, right?
Okay.
So I wouldn't say one's done before the other because they don't really impact each other. Right?
True, but when you're building up expressions, especially like you're dealing with like functions that take in functions and you're composing them, right?
Right.
The evaluation order is going to be treated as where the first data argument's passed in, right? And based on that example, if I understood you correctly, you're saying that the parentheses is basically building the final function that's taking in C as an argument, right? So whatever C evaluates to, it's going to be passed into AB.
The result of AB, that's correct.
Okay.
So I view it more as it's an iterative process, right? And so you can count them in kind of step 1, step 2, step 3. And these parentheses show that in step 1, on the left, in step 1, AB would be evaluated simultaneously and separately from C, and then they would be applied, right? Whereas on the right, A would be just, we would recognize some value for A, and then the expression BC would be evaluated simultaneously and independently of A, and then they would be combined.
Got it.
Right?
Okay.
So here's some valid expressions. We can have just a symbol like A, pardon me, my phone, which is just an abstract value. Doesn't necessarily mean anything in particular, but it's useful for in evaluation. And then the next one, lambda a dot axy. This is a function basically with one parameter. So there's one lambda symbol, or one lambda symbol, and then another identifier symbol. In this case, a, that is serving as a parameter, or as in most in computer programming languages, that would be a variable name, and then a dot, and then the expression axy. And axy in this case is called the body, and it is what will be evaluated with respect to the value that comes in via the parameter a. The next one is we can stack up. So lambda, every time that we use a lambda operator, it basically consumes one parameter symbol, one period, and perhaps some parentheses, and then there's some evaluation done, and then it returns a new expression. So in this one, lambda b dot lambda c dot bcb can be viewed as either a function that takes one value via the parameter b and then returns a function that wants to take something via the parameter c, acting on the body or applying to the body bcb. Or another way of looking at it is it's one function that can take in two parameters and then evaluate bcb. Okay? And then the next example I have, lambda d dot lambda e dot dedc, is similar to what we discussed one slide ago. So the sub-expression ed would be evaluated simultaneously with values being passed in or substituted for d and c. Then on the next one...
could you explain a little bit about what you mean by parentheses to specify precedence, please?
Sure. If we're going to take in the body of this expression, e left paren, ed right paren c, the value inside ed would get evaluated before whatever that evaluates to gets applied to d. Right, so d could somehow operate on e. Right, that's prevented with these parentheses. Right, so the d to the left cannot apply to the e to its right because of those parentheses. So e can be applied to d inside. I should use yet more symbols in here to make this clear, but ed must be evaluated before it is evaluated in conjunction with c and d.
Got it.
Right?
Okay.
It's somehow deeper, right? It's precedent, right? So the evaluation inside there has to occur before evaluation of the larger expression. Just like in mathematics, right? We can have 1 plus 2 inside parentheses that then gets multiplied by 5. And it's not 2 that gets multiplied by 5, it's 3 that gets multiplied by 5. So evaluation goes from inside to outside, like in arithmetic. Okay, then the next one, which is, this is now a function with an input value. So the input value is x. So if we view this as everything inside the parentheses is a lambda, it's an abstraction that has two symbols that will act as parameters, and then a body, PQP, which is basically the body of the function. And then x happens to be an instance of some input value to be used by that function, right? So this is just, I'm showing that the lambda abstraction can be written by itself, like in the second and third cases on this page. We have abstractions that don't have the parentheses around them because they're not really needed, right? But then there's nothing to separate them from. But in the 1, 2, 3, 4, 5th row here, lambda p, lambda q, pqp, in this case we are using the parentheses to show that conceptually and usefully, this abstraction, starting with lambda p and ending with qp, is something, and then it will be applied to a value x, right? And so now we're bringing in some value to be used in the evaluation of this lambda abstraction.
I have one question. Are
Okay.
these expressions, are these lambda expressions anonymous? Are they are their name they're basically anonymous functions, right? These are they don't have a label associated with them.
Everything that we've done, they don't need them,
Right.
and everything that we've done through this slide is anonymous.
Okay.
There's no reference to any particular function named cosine or anything like that. There are only basically instructions as to how to carry out an operation.
But the lambda calculus does allow us to name lambda expressions, yes?
Yes, that's frequently done. You don't need to do it. And at the end of this presentation, I'll give some links to cases where my favorite was a person programmed FizzBuzz completely using anonymous functions, right? So he had to come up with he had to use an encoding for integers. He had to use a way of building a range. He had to use a way to iterate over the range, et cetera, et cetera. So lambda calculus at its most fundamental is completely anonymous.
Cool.
Now, it's very useful for reasoning and to save pencil and eraser to be able to give shorter names to long expressions. And we'll see some examples of that. We'll work with, I think, true, false, not, and or. Okay, so
thanks.
This lambda, so an abstraction, what am I showing in the one starting with lambda r, the expression, which starts with lambda r and ends with yx, paren, can itself contain a lambda expression. So in this case, the value a would be bound to the parameter r, and then every instance of r in the expression to the right of the first period, which is lambda s dot r, left paren, lambda x dot yx, paren, the r in there would be replaced with an a, right? So the point here is that lambda functions themselves are first class, both in the bodies that get evaluated and also in the values that get passed in via parameters for evaluation. So the very last example, lambda m, lambda n dot mnm. Now that is an abstraction that takes two parameters, but the very first value that it will receive is the expression itself, lambda x dot yx. So that would be during the first step of evaluation of the expression, the abstraction on the left, the lambda expression, lambda x dot yx itself would be substituted in for every occurrence of the symbol m in the expression lambda n dot mnm, right? And we'll walk through this. It's confusing, but I want to show that these are what valid lambda expressions will look like. And then here are some invalid ones. We can't just have the lambda operator floating around by itself. It must have a parameter and then a body. So the second example shows that, okay, if we have a lambda with a symbol to use as a parameter and then a dot, that's everything, that's fine so far. But then there needs to be an actual body for that parameter to be fit into, right? So a dot must be followed by an expression. In this case, not by another dot. The next one is an example of, to be careful, we should always have a lambda symbol and then the lambda operator and then a symbol and then a period and then some expression, which might itself be an abstraction. But in this case, I should have put in a period between d and lambda, right? And that's just simple grammar. Next one, lambda a dot dot a. The two periods cannot adjoin. They do. That's a repetition of the second one. Yeah, they can't be next to each other. And then, like in everything else, in the final example, parentheses to be useful have to be balanced. Otherwise, they're confusing. So here is, I've used the word abstraction a lot, and it's one kind of expression, and it's more precisely defined. And it is exactly the symbol lambda followed by some identifier, which could be a single letter or could be a capitalized string or something else that we can clearly identify and separate from other symbols. And then a period that's used to divide the left-hand side, called the head, from the right-hand side, called the body. And then the body itself is an expression, but not necessarily an abstraction, right? So a very simple example is the abstraction lambda a dot xay. So we have the symbol lambda, which is the operator, and then the symbol a, which is used as an identifier to be used as a parameter to perhaps take in some information. Then the period, and then the body of the abstraction, which is the string of symbols x, a, y. So if we were to use this and take in some value, now we can view this as a function that has one parameter. So if we pass in, for instance, the value tiger, then a would be replaced with tiger. And so we would have x tiger y, right? So this then shows there's lambda, parameter, divider, and body. And the head portion is everything to the left of the period, and the body is everything to the right of the divider of the period. So that's it. And I'll just go back and show, this is an abstraction, which is one specific kind of expression. So the grammar here on the 1, 2, 3, 4th line, starting with lambda, there'll be some identity, and then a dot, and then an expression, right? So that is the subset of expressions that are called abstractions. Okay, now to evaluate, we do this thing called evaluation of the body of an abstraction. The kind of the heaviest step is one called data reduction. And in this step, some parameter is bound to or tied up with the first expression after the body of the abstraction, so the first input value, basically. So it's like a function call with some parameter, and we take in a value to the function via the parameter and then act on the body of the function. So every instance of the parameter symbol in the body is replaced with the bound value. And then the lambda operator, just as bookkeeping, the lambda operator, the period in unneeded parentheses can be removed. So here's an example. If we have the abstraction lambda a dot ax aya, right, then that gets past the value f, right? Then the value f is bound to the symbol a, because a is the parameter of this lambda abstraction. And then every occurrence in the body, which is everything to the right of the period, every occurrence of a in there gets replaced with f. Right? So parameter a is bound to f, and that's often written as a, I guess that's walrus, f. Right? In the body, ax aya becomes fx fyf. Okay, so earlier I said that every occurrence of a lambda has to have one identifier and then a period. But just for convenience sake, the decision was made early that, okay, we can abbreviate this stuff because there's too many lambdas and too many dots rolling around. And so the rule they came up with, which is consistent, is just that every time you can delete every period except the rightmost, and you can delete every lambda except the leftmost. And then all of your parameter symbols or identifiers just collapse into a list, basically. So lambda a dot lambda b, I'm sorry, I'm talking to the wrong slide. Okay, if we have multiple heads, then we have a lambda that's going to take one parameter, and then the result of its evaluation will be an abstraction, which is a lambda that itself takes another value via parameter, etc. And so in this walkthrough, lambda a dot lambda b dot lambda c on x a y b c b, taking the input ftr. One step, if we take a and bind a value f to a, then we can replace in the body, which in this case is x a y b c b, and we end up with x f y b c b. And the parameter a has been discarded, one of the lambdas has been discarded, and the input value f has been used up, right? So this, then we have a lambda abstraction, which is waiting for two more values via parameters b and c, and that the evaluation can continue. It does not on this slide, so we're not done yet with this one. But that just shows one, explicitly one step of taking a value f from some string of values, some stream, I guess, of values, and binding it to a symbol a, and then using that in the evaluation of the expression, and then moving forward, right? So that shows one step of evaluation of an abstraction that expects three parameter values, a, b, and c. Okay. So here's what I was talking about. As syntactic sugar, the lambda r dot lambda s dot lambda t in this slide can be simplified just to lambda rst. Right? That is purely notational convenience, but can make things easier to read sometimes. Okay, an important thing is the counts of parameters and values can differ. And this, if you think about it, goes back to the fact that, well, sometimes we want kind of non-functional outputs, and sometimes the output that we want is itself a function, which must be some lambda abstraction that has a parameter or more, one or more parameters. So in the first case, lambda a dot xaya fgr, it is basically a function that has one parameter a. And then first step in that is, okay, we bind a to f, and then we replace all instances of a with f, and then we don't have any, the result of evaluation of that expression is simply a string with no lambdas. So there's no further parameters to take in values. So at this point, evaluation halts, and we end up with the output x, f, y, f, g, r. Okay? Then parameters might not occur in the expression applied to a value. So in this case, if we have the lambda abstraction lambda g dot xby, if you look, the symbol g, which is the parameter symbol, doesn't even occur in the body of that abstraction. So no matter what value gets passed in to be bound to the parameter g, it has no effect, because there's no occurrences of it to be replaced. So lambda g dot xby applied to f is xby with every occurrence of g replaced with f. But since there are none, nothing actually happens. So we end up evaluating straight to the body of the abstraction.
Hey, George, can I just mention one thing here?
Yes.
So for folks looking at this expression, wondering, is this even a valid expression? It is a valid expression. Specifically, it is a valid expression in the sense that x, b, y are what are called free variables. All right, free variables is a concept that basically says that a lambda expression does not necessarily need to clearly include in the body every variable that was declared in the head. That and allows us to write things like, say, in the most simplest of cases, like an expression that, like, returns, like, say, a constant function or a constant variable that's completely separate from what's being passed in. This enables that kind of expressions being available in the Lambda calculus. Um, I don't know if you have another example of this where you introduce free variables, but I thought I'd mention it here because this clearly shows free variables.
Okay, I might or might not. I don't think I do in the remaining slides, but that's a great point. And the usefulness. So 2 points that are brought up. One is I can define using a simple lambda expression some function that will always return a constant value. I can give it some value like 3, and it might be lambda x dot 3, right? And then no matter what gets passed in as the value of x, it doesn't occur in the body of the expression, so it's just simply discarded, and 3 is returned. And that is one way to implement constants in the lambda calculus using interestingly, purely functions, right? So I now can use a function to return a constant value, which is interesting. Then on the other hand, we should be kind of comfortable with the fact that these expressions, since the values passed in via parameters to abstractions can be, but don't need to be, lambda expressions themselves, we can use these, and we do use these, to build up more complex functions. So at this level, we just say, oh, the result is x, b, y. But at some higher level, x, b, and y might each themselves have very important meanings in the context of a larger abstraction, right? So in this case, from the perspective of this lambda abstraction, x, b, and y are all free variables. And f is bound to g but then discarded simply because g never occurs in the body x, b, y. So we'll see 1 or 2 examples of building up functions that make use of free expressions from smaller or contained abstractions. Okay. So another thing that we should think about is lambda expressions can occur in the expression that's applied to a value. So what do I mean by that? Okay, if I have an abstraction lambda a dot, and then lambda b dot, and then parentheses a, b, and a, and then that is taking in values f and g, then a will be bound to f, but then the body of the lambda abstraction that made use of a itself contains a lambda abstraction. So we'll replace every occurrence of a with f, and now we end up with a new lambda expression, lambda b dot fb f on g, right? And then what do? Oh, now we have a function that has one parameter b, and it's going to operate on the body fb and takes an f, right? So what do I get here? B grabs g as its value. So b is bound to g, and then occurrences of b get replaced with g. So fbf becomes fgf, and that's the result of the evaluation. So again, the important point here is that we can and do stack up lambda abstractions inside the bodies that are evaluated. Okay. And then similarly, lambda expressions can actually call that abstractions can be passed in. So if we have an abstraction lambda a dot axb, we could, and here do, pass in as a value another lambda abstraction lambda b dot b. right? And then there's another value f kind of in the pipe waiting to go. So then here's some notation. So we can say, okay, the body AXD, and then the square brackets are used to explicate that A is bound to the value, which is a lambda expression, lambda b dot b, right? And then every occurrence of A, of which there's one, gets replaced with lambda b dot b in the expression. We got lambda b dot b x d applied to f, and then f gets bound to b, and b happens. Our lambda expression happens. Lambda b dot b is just the identity, so b gets replaced with x, and we end up with x df. Okay. Then
so
alpha.
can you go back to that last slide again?
Sure.
Why is that not fxd?
I'm sorry, what?
Why is that not fxd as the result of that beta reduction?
Because, let's see. Did I make this mistake?
Oh, right. This is what we talked about last time.
Maybe I'm missing parentheses here.
So here in this first, if I may, I'm pretty sure I remember this example. He passed in the identity function, okay, and replaced the a with the identity function. So now it's lambda b dot b xd, right?
Yes.
So I think there's a missing set of parentheses around lambda b dot b, and then
You're right.
xd.
There are. Let me fix this because we did talk about this last time.
Yeah. So
I'm embarrassed about that. So
not a problem. But I think you have to go further down. A couple more. Keep going. One more. I think it was, yeah, right here.
Yes, the magic of parentheses.
Always changes the meaning of an expression. You know?
Yes, that's what they're for. Okay. Is that good? Are we okay?
Yeah, so in this case now, with these parentheses, you can clearly see what's actually being passed into this identity function is x to b. So that means b is now substituted with x, and that becomes xdf instead of fxd.
Okay, so you also need, where the assignment to A happens, then you also need the parentheses around the lambda expression there too?
No.
You
Where you're doing the binding?
You don't, but you can. This is where the case where, because it's a left associative, oh crap. Because of left associativity, those are kind of assumed, but they can be explicit too. So you're right. Okay. Thank you. Great. Okay, so alpha equivalence is used to deal with the fact that we're using abstract symbols, and they might not mean the same things in different contexts. So specifically, the only meaning of a symbol in a body of an abstraction is basically a place to take a value passed in via a parameter in that abstraction, right? And it's similar to, like, namespace collisions in packages of software. If I say something, if I name something foo, but then I start making use of some functionality that uses foo for its own purposes, we need to be careful about using the symbol foo. So in this example, lambda bc dot b and lambda xcx, the only meaning in the first case for b is that the symbol in the body B should be replaced by whatever's passed in down to the symbol B in the parameter list. And that means that if I take the first one, lambda bc dot b, and apply it to something, I'll get exactly the same result by applying lambda xc dot x to whatever my input was. Because, again, the only purpose for the symbols in the body is to take values passed in via parameters. Right? So the b in the body doesn't mean anything other than, give me the value that's passed in by a parameter b. Now, on the other hand, the two lower ones are not alpha equivalent, it's called. So lambda c dot af is not the same thing as lambda c dot az, because we don't have any, there's no, if this abstraction were to get integrated into some greater abstraction, then we can't be sure that f and z actually are equivalent. They might mean very, very different things, right? So that's kind of basically variable scoping. If I just say, if I name all the variables in my package as foo, I can't count on some other software making use of my package respecting the use of foo, right? So we can do something just called alpha conversion. So if there's a value has the same symbol as a variable occurring in the body, right? You can read this as fast as I can. Then what we need to do is just very simple substitution. So in the expression lambda ab dot ab on b, it looks like it might, we take in the value b, and then replace all instances of the symbol b in the string ab. So it looks like it might actually simplify down to lambda b dot bb. But since we're being careful, we have to notice that, well, the two orange b's are related. They have some linkage, right? Whereas the black b does not have any doesn't have any particular relation to the other symbols that happen to be b. So it's bookkeeping, and tools can just go through and scan for that and find out that, oh, these symbols could collide, so let's replace one of them. So this simple solution is, okay, let's just take every orange B and replace it with the letter Z. And so now we end up with the abstraction lambda Z dot BZ, which is quite different from what we had earlier. Does that make sense or not?
Yeah, I think that makes sense. The only comment that I have is the lambda ab dot ab applied to b. You're doing left to right a substitution, right? So b is actually substituted with a, right? B is so in the for example that you have there, b is substituted with a, and then the one lambda is down, right? Okay, just want to make sure that I'm not misunderstanding that. Okay, cool. All right.
Thank you.
Yeah, no problem.
Okay, then the next point is parameters that are identified don't necessarily need to occur in the body. And we've seen this in a couple examples before, but in this case, if we have an abstraction lambda a dot cd taking in the value of x to be bound to the symbol a, then a does not occur in the body at all. So again, a is simply discarded. So lambda a dot cd on anything, applied to anything, will result in the value cd. So it's constant. Then we might end up binding all of our parameters before we run out of values. So in this case, we have an abstraction with 2 parameters and 3 values. So 2 parameters are A and B, and 3 values are D, E, and F. And then if we apply, then we bind D to A, and then bind E to B, and end up with D, C, E, F. And that's it. There's no further evaluation to be done. Similarly, we can run out of values before we run out of parameters, right? So we could have, in this one, there's 4 parameters, A, B, C, and D, and 2 input values. The result, we end up with a lambda abstraction with 2 symbols acting as parameters on a body, right? So 2 ways of looking at that are, okay, the result of the application of our input is to generate a function that takes 2 parameters, or equivalently, we could say, okay, we will result in a lambda abstraction that will take 1 value and then generate a function that will await a second value, right? So this is partial application. So we might, we might want to generate a specialized function based on some input in order to maybe save computation time or something like that. In which case we can pass in parameters to build the function, and then end up with the function as a value, store that, and use it somewhere else in software, right? So perhaps we have some incredibly specialized geometric function, and it will help us a lot if we can narrow it down to one very, very small subset of values. So we might generate a specialized function that already has those very specific values passed into it, so that we can store a function to be used later more efficiently. So we can take inputs and generate functions as output. And then, okay, what can we do with lambda calculus? And basically, everything that is computable in this sense, right? I think that the concept that's been around is Turing complete and NP and NP complete, and hard and things like that. Basically, anything that can be calculated via an algorithm can be encoded, at least in principle, in the lambda calculus or on a Turing machine. So what's beyond that, I think, are what's referred to as oracles, actually, which are just some kind of mechanism that can take an input and then, without even applying an algorithm, give you the correct output. But this is the kind of the limit. Lambda calculus and Turing machines and mu recursive systems are equivalent. Okay, so here's an example, and I think this is better this week than last week. So a normal encoding, since we only have functions themselves to pass around until we start adding labels, which we'll do right now, deep down, we need to encode specific values as functions. So the normal, they're called church encodings. For true is that first abstraction, lambda AB dot A. And then false is encoded as lambda AB dot B. And those end up being useful, and they're nice because they're distinct, and they're in a sense, well, in a real sense, they're very opposite. So any lambda AB dot A will it will return the first value that comes in after that A, whereas lambda AB dot B will discard that first value and take the next value. So they act in opposite ways, right? So down at the bottom, if we have lambda AB dot A applied to RS, we'll get back R. And if we have false, which is lambda AB dot B applied to RS, we get S rather than R. So that's distinct and opposite, right? So here's a walkthrough of it. lambda AB dot A on XY. X gets bound to A, so then we end up with lambda B dot X applied to Y. So Y gets bound to B, but B doesn't occur anyway, so X is left there as the return value. Right? And then for false, it's the opposite logic, basically. A gets bound to X, so we end up with lambda B dot B, which is, again, the identity combinator. So anything that gets passed in becomes a return value. And so Y is there to get bound to the symbol B. So Y is what's returned. So in the first case, X is returned, and in the second case, Y is returned. Right? So now we can walk through building out a function in Lambda calculus. So not is a nice simple one to start with. And so not is going to be some function that's going to take one boolean value, and then return its opposite. So if whatever comes in is true, it returns false, and if whatever comes in is false, it returns true, right? So we kind of have not means, it would be a lambda operator acting on one symbol, followed by a dot, followed by some expression that will, taking into consideration the value passed in by the parameter, evaluate either to true or to false. Okay, kind of wordy, but we just call the value P for predicate, and we're going to make use of the church encodings of true and false. Okay, so not is the function, it's a restatement. Then, all right, so what we have then is P is going to be a Boolean value itself. We're going to end up really with a string of 3 Boolean values, right? If the first one is true, then we want to return false, right? Otherwise, we want to return true, right? So walk this through. If bool 1 is true, then that means that I need to replace the forward slashes with lambdas. Lambda P dot P, bool 2, bool 3 applied to true is equivalent to true, right? Which is encoded as lambda A dot A, lambda AB dot A. Right? It's equivalent to true bool 2, bool 3. So lambda AB dot A applied to bool 2 and bool 3 we're going to need bool 2 to be false because it's what's going to get returned by lambda AB dot A, right? And then we need to end up discarding bool 3 as a value, right? So the first step of evaluation will take lambda AB dot A, bool 2, bool 3, and evaluate to lambda B, and then I have lambda CD dot D, which is an alpha equivalent encoding of false, right? Onto bool 3.
So I have a question here. Lambda AB dot A.
Right.
When you're applying it to bool 2, so you're going to get lambda B dot bool 2, right? Which is essentially what we saw earlier. It's going to be lambda CD dot D in that case.
Correct. Right.
So we've effectively okay. So we're effectively creating another function that's going to return that function before we apply bool 3, sorry, to B, right?
Yes, that's exactly right. So that's the cool thing about the encodings of true and false, right? Is that we can use them basically as control mechanisms, right? So we're going to take in lambda P dot P. It gets passed in the value true, right? So every occurrence of P gets replaced with the function that is the true function, which is lambda AB dot A, right? So then that, the second line, it starts with this is, right? We've replaced P with true, and then changed true from its capital letter representation to its functional definition, right? So now it's lambda AB dot A. and we haven't done anything yet with bool 2 or bool 3. But we know, right, so the input to our test function, or not, was true. So we want the result of that evaluation of that to become false. That means that bool 2 has to be false. This is what's going to get returned by true, right?
Right.
That's the trick, right? True returns the first, ignores the second. So in the case of not, then we want the first thing to be false, so that we will correctly return false, right? So lambda AB dot A, bool 2, bool 3, we have to say, okay, bool 2 must be false, because that's what's going to get returned by our function that we're building, right? And then bool 3 could be anything at all, but it has to get discarded, right? So what that means is if we then expand, if we evaluate lambda AB dot A on bool 2, then we end up with lambda B on lambda CD dot D, bool 3. Now that's convenient because bool 3, whatever it is going to be bound to the symbol B, which doesn't even occur in lambda CD dot D.
Right, which means it will be discarded.
Right, and lambda CD dot D is actually just alpha equivalent. It's another way of saying false, right?
Right. Mm-hmm.
So yeah, so that works, right?
Right, that works.
Then, contrarily, if bool 1's false, then bool 2 is false, because we just decided that's what we have to define in our function. Bool 2 has to be false. Then bool 1 on bool 2 on bool 3 will go to true on false on bool 3, right? So AB dot B, right? So false on false, something else, discards false and takes the something else, right? Which we know we want it to be true, right? Because that's what false should return, under not, right? So, okay, bool 1 is, if bool 1 is false, then it's going to return the second thing. And we already know that bool 2 is false, because we just decided it in the paragraph above, right? Then bool 1, bool 2, bool 3 becomes false on bool 3, right? So the first lambda A B dot B has the effect of just discarding the first thing it sees, which in this case is false. And then we know, well, okay, we passed in false as our input to not, so we want the result to be true. The only thing that's left is bool 3, so bool 3 better be true, right? So now we've come up with our definition of not using lambda calculus. So not is lambda P dot P false true, right? And then, whatever we pass in after that abstraction is what should evaluate to some boolean value, and then it gets, appropriately returned. That makes sense? So, I worked through this after our last week, and just to make sure I understood it, but to actually build up the function not, well, we know that we have to take one parameter and then return one of two values. So luckily, the church encodings of true and false can be used as controls. So if I take in some value via the predicate, right, then, okay, I know that it's going to be either the function that acts like true or the function that acts like false. So the two things that I have to possibly return are either true or false. So in the first case, I want to return, if bool 1 is true, what should happen? I should return the first thing. Well, then that first thing better be true, which means bool 2 has to be true. And then just to make sure, I better make sure that that bool 3 actually gets discarded because it's no longer of any significance. And the function true does that. So this lambda AB dot A. So just completely discards B. There's no B there to worry about, right? That makes sense, AB dot A. So whatever gets passed in via B just gets completely ignored. So that's correct. That operates the way we want. So lambda p dot p bool 2 bool 3. The correct definition of not is lambda p dot p not false true, and that gives us what we want, right? That all makes sense.
So this is this an example also of essentially, because all these are functions, this is essentially we've effectively implemented not as a higher order function? Like, is this encoding?
Absolutely, yes.
Okay.
They're kind of, unless you're dealing with completely concrete values, every function in lambda calculus is, in that sense, a higher order function.
Got
right?
it.
Just by definition. Contrariwise, if they're not values, they are functions, and we pass them around all the time. So this is a case of using encodings of our concepts of true and false via functions in a way that's useful. I've kind of looked around for other encodings of true and false. I haven't found any. I haven't dug very deeply, but these ones do work, and they do very valuable things. So those particular abstractions, lambda ab.b and lambda cd.c, those show up a lot, right? And they're used as true and if and things like that. So there's a lot of things that look the same once you peel a layer of bark off. Okay, so let's go through, right? So we have not, which means we've defined it as lambda p.p on false, on true, on something, right? So we'll say our input value is x, which we'll say is true, which again, to remind everyone, is encoded as lambda ab.a. So then I blew this stuff out horizontally to show like what's getting manipulated step by step. So not on x is not on true, which is lambda p.p, false true on true, right? And then we take in, okay, an alpha equivalence for true is lambda gh.g, right? So that's equivalent to lambda ab.a, just because, g is a and h is b. So then that's the value that we're going to pass in and bind to the parameter p. So the next step is, okay, we have the expression p, and then these square brackets come in handy, where p is bound to the abstraction lambda gh.g, followed by true, followed by false. Is that right? No, it's false followed by true, right?
Right, that's right. In the case of not.
Okay, so p goes away and gets replaced by this abstraction that's followed by two more abstractions, which are really secretly the encodings that we have for true and false, right? So then lambda gh.g reduces to lambda h.g with g being bound to false, right? And then that followed by the value true. So that results to lambda hab.b on true. And so then true gets bound to h, but h doesn't even occur in the expression, right, in the body. So it gets discarded, right? So then we end up with lambda ab.b, which is false. That's our definition of false, is that function, right? Pretty cool, I think.
This is really neat.
I think it's...
I'm always astounded by it, just because it all works out just by simple substitution.
It just falls out, and you're like, well, yeah, I guess that is false. Okay, I see.
And folks watching, if you go back to that slide, he's using the shorthand again for the multi-parameter function, the multi-parameter lambda expression.
Right here. Yeah. Okay. So then we, in case we don't trust ourselves, we can try it out the other way. And we get not, again, is defined as lambda p.p on false on true. And we're going to, in this case, say x is false, which is encoded as lambda ab.b, right? B being the second thing, the second parameter that comes in. So then we have not on X, which means we have not on false, which means we have this definition we just came up with, lambda p dot p, false true, on false. Then again, I use alpha equivalence. Let me make sure I got these right. So lambda p dot p on false, that's correct. On true, that's correct. On false, that's correct. Okay, good. So now we go through the body, which is simply the string true, false, true. And then we've substituted in the encoding of the function false for p. So now we get false, false, true, right? So now we're down at lambda h dot h row, and we have bound the function false to the symbol g. And again, g does not occur in the body of the abstraction starting with lambda h at all. So that the value false actually just gets discarded, out to dev null or wherever. So the only thing left now is lambda h dot h and the encoding of the value true. And as we've discussed a few times today, lambda some symbol dot that same symbol is the identity function, the identity combinator. So identity on true just evaluates to true, right? So we're done.
Very nice.
Everybody there? I think it's slick. I like it. Okay, so similarly, we're not going to go through deriving it, but or is a function that it takes two Boolean values and returns true if one or both are true, false the otherwise, right? So we could end up writing this, right? Or is some abstraction that takes two parameters, p and q, and then has a body that does something, right? Turns out this will do it, right? Lambda pq dot p true q, right? And we can work through it. So let's set, we have two input parameters, p and q, and we'll set one to false and one to true, right? So we can say, okay, lambda pq dot p true q on false and true. Then the next step, okay, we take false and replace all occurrences of p with false. So now we end up with lambda q on false, true, q, right? So now true is going to get bound to q. So now we have lambda q on lambda ab dot b on true. Again, that's the encoding of false. Lambda ab dot b is the encoding of false on true on q. So then we end up with, okay.
So you're discarding the first q, and you're essentially getting two applications of the identity in this case.
Yeah, it turns out that in this case, evaluation kind of in either order, they're equivalent, right? So lambda ab dot b on true, I can just crush that into lambda b dot b, which is the identity, right? And then, okay, lambda b dot b on q just evaluates the q, and then lambda q dot q, the only thing that we haven't pulled in from our value stream yet is true.
So I have a question here. Isn't lambda pq dot p nothing more than alpha equivalence for true? So isn't that just true, true, q?
Yes.
Okay. Could you go back to your previous slide?
They mean no more and no less than exactly what they mean, but you're absolutely right.
Could you go to the previous slide? I want to make sure that...
Oh, sure.
When you're building OR.
Build OR?
Yeah,
okay.
When we're building OR, the definition here. PQ dot something. And then if you go to the next slide, you did lambda PQ dot P true Q. So really, this is just true, true Q, right?
Correct.
Okay, all right. Just want to make sure that.
Okay, yeah. If we think about it that way, right? If we go like, okay, it's true, true, Q. So the first true eats the second true, but then just becomes true.
Right.
Because it's the that's it. So the first value applied to the true function is the function true. Now we're left as the result of the first level of evaluation the function true applied to q.
Right.
And the only way that, if q is false, then that means one of the two was false. So it should return false, which is exactly q. Whereas on the other hand, right, if q is not false, and it doesn't even matter that it's true, right, true will return true, right?
Right. It's like short circuit evaluation, right? Because
yes, it is.
First thing is true, it returns the true value that you have. Otherwise, if it's false, it returns you whatever the second thing is. So if that's true, then the whole expression is true. If that's false, then
yeah. It's a lot like short circuiting. It's just that in these cases, like we've drilled through. It's like even if the little monster inside my computer wants to actually evaluate everything, these things are set up such that it has to discard it according to its own rules, or it has to keep it.
So you're getting short circuit evaluation for free by essentially encoding it this way, essentially.
I think so, yeah. I mean, I don't know if that was their goal, but certainly these things, they're I heard the word isomorphism like 50,000 times yesterday, so I don't want to say it anymore. But these things look very similar, right? True and control. This is how we must do it this way, right? Deep down, it's only just electrons. So, all right.
They're just isomorphisms. I don't see what the big deal is.
It's just a mono in the category of endo functions. What's the big deal? All right, so let's try it out. Did we do this? We did this, right?
Yes, we just did this.
Okay, so here are some cool things that I've found out, right? The online tutorial with REPL is available right there, and that's different from one of my earlier versions of the slide deck, because the guy actually changed his domain name in the last couple weeks. And then a flock of functions. This is some very cool stuff. There is. I'll turn on my camera and hold up my book. Right, I have this book. Do you?
No, I wanted to order it. It's a pretty in-demand book.
Turn this on. Okay. What do I do this? But anyway, never mind. I can't figure it out my computer. The book is called "To Mock a Mockingbird," which is one of the fifth or sixth point in this slide, and it's by a guy named Raymond Smullyan, who he's passed away unfortunately, a philosopher, and he ended up writing a bunch of puzzle books. But what he does is his puzzles are stories about the guy wandering off into the forest. So in this particular forest, there's just all these birds, and the birds they'll sing songs, but each species of bird has a different rule for what song it's going to sing, depending upon what it hears. And so this, metaphor of birds and magic forest and all that stuff, each of the bird species is actually one of a set of what are called combinators that Ram alluded to earlier. And a combinator is an abstraction in which there are no symbols in the body that do not occur in the parameter list, right? So in a sense, or I think the way I think of it is, they have enough information to consistently give you exactly the same result each time. And that, of course, is a very deep thing in functional programming, right? That's referential transparency, right? So you must have enough information, and there must be no additional information that could skew the result, right? So those are combinators. And so To Mock a Mockingbird has a bunch of puzzles about, well, what happens if this bird talks to that bird, right? There's blackbirds and kestrels and kites, and then the famous one is the Mockingbird, which I think is the Y Combinator, but I'm not sure. And then I guess one thing I didn't talk about, let me try to do this, was the fact that some abstractions cannot be terminally, they can't end anywhere. So let me try to get here.
Are you talking about the recursive?
Yeah.
The one that's
infinite is how to implement recursion using an iteration, right? So this, can you see this Lambda Explorer?
Yes.
Okay, so
Could
here
you
is the
increase the
website.
font size though?
Okay, hold on. Okay, is that better?
Yeah, that's better.
Okay, so straightforward URL, and this does have a tutorial that's pretty similar to what we just walked through, and it's a REPL, so we can type things in here. Just say, how does A evaluate? A evaluates A. I don't think this will work. Yeah, okay. It doesn't want to see numerals. It'll see symbols, and it's saying like, look, I'm not even promising you that these mean numbers. I'm just telling you these are abstract symbols that evaluate this way. So then I can say lambda A. Okay, let's do true. Let's see if it even knows it yet. Lambda A B dot A. Okay, so deep in this application, he's already taught it that anything that looks like this symbol occurs here once and only once, and this doesn't ever occur, that thing ends up meaning true, right? So it's evaluated and it says if what you want out of this is the church boolean encoding, it happens to mean true. And if I go, okay, lambda a b dot b, right? Okay, that's the false, right? And you'll notice it also says the church numeral 0, right? So there's another incredible talk where a guy ends up writing FizzBuzz using only lambdas. I think he did it in JavaScript. So whatever they call lambdas, right? He built from the concept of 0. Then he said, okay, well, to get any other numbers from the numeral 0, then what you end up doing is, so we can say like 0 equals like x, right? And then 1 is actually one application of a function to a value, right? And then 2 ends up being 2 applications. So 2 means the same thing as twice in this encoding, right? Which is how you can control how many times you do something, right? On x, is that right? Yeah. So those would end up, those would be the encodings of 0, because I've applied f 0 times, and 1 or once, which is one application of f to x, and then 2 or twice means 2 iterations of f onto x, right? Does that make sense? That's really cool, because then you can do that with a comparator to, so next is pretty easy to encode. Just apply f to whatever number came in, right? But predecessor is harder, but it's only basically, we'll keep going until you get to what you're trying to decrement from, and then give me the first, right? It's a little trick, right? It's like, okay, keep going until you're almost there and then stop, right? And it works out. So he can then iterate through a range of encoded numerals, right? So he's got to go from the number 0 to 100 and either print out fizz or buzz. And he does all of this using lambdas. So, of course, he starts using capital letter strings to help make it easier for humans to read. But then at the end, he goes and searches and replaces everything and blows it all back down into lambdas, right? And then he runs it, and it takes like 3 minutes to run, right? But he does end up with the correct output for FizzBuzz from 0 to 100. Pretty nifty. So that is in my slide. Oh, maybe it's not.
I think you took it out.
Okay. Well, flock of functions is great too. And then Y Combinator is a coder I've seen on a lot of videos who really likes Ruby. And he basically just walks through building the Y Combinator. And the Y Combinator, again, is this. Let me go up. This. Now, if you look at this, what this means is, okay, I'm going to take in something and pass and bind it to the value g, to the symbol g. So I'm going to take this part over here, right, and then bind it to g. But if you look at that, what you end up with, it will evaluate to itself. So it goes on forever. So, sorry for coughing. How this can be used is whatever we put over here will kind of get called, it will recur forever unless in its definition itself it says in some condition halt, right? So this can be used to recursively do things or iteratively do things, saying like, okay, if my termination value is 100, then I'll just recursively do it, and what I'll end up building is the function that goes up to 99, and the function that goes up to 98, and the function that goes up to 97, the function that goes up to 96, and eventually it'll be the function that goes up to 0. It's like, oh, that's too big, and then it will give me the alternate evaluation, which is the terminal clause in the recursion. So if we try to take this guy right here and put it into, oh wait, just to prove that my stupid joke is real, right? If I put this guy, recognize this? That's right, that's not. So if I put this in here, probably, let's see, bad number of arguments, why that happened. Lambda p, okay, take that out. What? Okay, let's try this.
Hold on. Can you go back to that? I think
Sure.
I figured out what it was. Yeah, there's a dot between the AB. Lambda dot AB dot. Get rid of that dot there in the last parentheses. Yeah, right there.
Man, another typo. Okay.
Boom. There you go.
Okay, it's a function. And so now in this little REPL, we're allowed to say this. Not, has to be all caps. Equals. And make sure I got that thing out of there. So let's see if I can do this yet. Not true. I might not have bound it to the string. Not true.
I don't think you have true defined.
Right. True equals lambda a b dot a.
Right.
Okay, so now, not true. Okay, I had not yet given it the string, so if I say false.
Well, it says church boolean false, so I'm assuming that it
Right.
recognized it.
Let me see if it'll do it. False equals lambda a b dot b. Okay. Not true. No, it didn't. Okay, but it does say, it's come back as, anyway, so I proved that my first slide is correct, except for this stupid typo, right? Okay, so let's try this. What do you think's gonna happen?
It's gonna complain.
Yeah, because it's stacked out basically.
Yeah, originally I thought it was gonna complain because he had a typo or something in there.
Right.
Nice.
That's what it ends up evaluating to. So then, the idea is that we have something out here that could potentially terminate, and it gets passed in. And so each iteration through, the function is actually check for the termination condition, and if so, give me the correct result, otherwise continue, right? So this is the Y combinator, and its close cousin is the Z or Z combinator, and they are used for the same purpose, but they need to be used depending upon whether we're using greedy evaluation or lazy evaluation. And I think that Y is greedy. So it's trying to evaluate things that come into it kind of before applying control. Whereas lazy will only evaluate things once the algorithm says it needs to evaluate, right? Am I making sense? So what's blowing this out is that exactly that the Y Combinator calls itself, right? So just like in the case, the standard example for Lisp is why we cannot define if as it has to be a special form, because we might never want to evaluate the second thing, because it might not even be valid, right? So never ever try to evaluate something that's, well, at least strongly avoid trying to evaluate things that might be wrong or might be badly formed, right? So if can ignore things that are badly formed, but it can only do that because it's not a regular form. Because in Lisp, all regular forms evaluate all the things that come passed in, right? So if it's going to greedily evaluate them, it's going to break. So if won't work, right? Does that make sense? So
I just want to mention for the Lispers in the audience, if you're interested in understanding the Y Combinator, Richard Gabriel, a very well-known Lisper, he actually was the founder of Lucid Incorporated, and they made, amongst other things, Lucid Emacs, which ended up becoming XEmacs eventually. He actually wrote a very good paper on the Y of Y, like understanding the Y Combinator using Common Lisp. I posted the PDF link actually for folks on the Hangout in the chat. For folks watching the stream, I will also post that same PDF link in the YouTube description, so you guys can also understand that. That's another way to get it. So there was a question about will today's slides be posted somewhere?
Sure, I'll do that. I'll put those. Where would be best, Ron?
I think let's just make a Haskell workshop like GitHub repository, so that way if we have presentations, we could just throw it in there.
Okay, so then you and I can decide where we'll put stuff.
Yeah.
And then let's put a comment in, I guess, the YouTube channel to say this is where we decided to put stuff.
Right, and for folks in our meetup, I'll also announce it just so that you guys can get the URL ahead of time.
Sounds good. Cool. All right.
Other questions from our audience? Feel free to ask away.
Oh, thanks for doing this. I definitely need those slides. I got to study.
Okay, cool. No problem at all. Yeah, it's a lot of fun.
It is. Yeah.
I mean, you just kind of looking at that, right? You see all these G's up on the slide? Okay, so it's recursively calling itself, right? So it's returning its first value. Interesting. I like it a lot. Okay, I don't have anything else, but, I'll sit and talk with people till the cows come home.
So there was one thing about that I wanted to at least ask, which was we covered kind of like the simple examples of like beta reduction, alpha equivalence, what evaluation is, and combinators. But I read somewhere about something called eta reduction. Do you have any idea what that is, and could you explain that?
Yes. And, see if I can focus it. Basically, it's if anyone is familiar with the concept of point-free definitions of functions, it's something like, see if I can do this off the top of my head. If I have some lambda that takes x, well, actually, I guess maybe even the identity might be one, right? What's going on? I'm trying to get my caps off. Is this Z? Let me try. Okay, it is small. Okay, lambda A dot a on something is going to return whatever I pass in, right? That's the identity combinator.
Right. Mm-hmm.
Again, a combinator, okay, combinator, everything that's in the body, which is just the letter A here, also occurs in the parameter list, right? And so now we know we have enough, we will receive enough information to come up with a consistent answer every time. So we have referential transparency. So if I say lambda a dot a on C, I should get back C, right? Okay, cool. So let's see if it tried doing another cool tool here is it explicates it, right? So a to reduce, it says it's irreducible. So if I have some, my recollection is a to reduction is, I don't see it a lot, but it's when something is kind of irrelevant. So we have a symbol that's both a parameter and in the expression, but inclusion of the value doesn't change the a to reduction. Doesn't change the output, right? So it can kind of get ignored.
Right.
So,
it's because I think if I understood it correctly, is given a lambda expression and an argument, you're just returning essentially the expression and the argument, right? So since you're returning the expression with the argument bound to whatever the first parameter is, so an example of it is if you do lambda a dot some sort of lambda expression that you're returning like lambda b dot b, and you pass in an argument. So essentially, the first expression lambda a is returning an expression lambda b dot b, which is the identity. All right, and you've applied that to an argument, say, and then you have also a in the expression, so it'll be lambda a dot lambda b dot ba. And if you apply that to an argument, like let's say C,
I called up the first thing I found, right, by some guy named Kevin Sukochev.
Could you just go to Lambda Explorer for just 1 second? I think this is just a pretty simple thing to go through. So type in lambda a dot lambda b dot ba. Okay, so given this expression, okay, so this is a function, okay, but it's an expression that returns an expression, okay. If you evaluate that with an argument, say C, okay, what you end up getting is essentially an expression applying to an argument, okay. So my understanding is that's the same as that is the same as the expression itself being available. So you can actually lop off one expression because it's meaningless. It doesn't actually help with the evaluation of the argument. Although in this case C is a free variable, so really what it should be is you need to add some more parentheses into it.
Here's this guy's explanation. So a to reduction allows you to convert between some expression like lambda x with the explicit parameter x on the body f onto x, right? We can convert between this whole expression right here and just the symbol f, right? And the reason we can do that is because, well, all right, for any x, we're going to end up with f of x, right? So for anything, we're just ending up with f.
Right.
So in this is the point freeness of it, and I didn't understand what point free meant. I thought the point in point free was this guy, and it's not, right? It's basically trying to the idea that fit with me was, okay, fine. Let's say that you have some integers out there in your headspace, right? And you're thinking them of discrete points on some line or in some space, right? And then you have some function that's going to multiply all of them by 2. So whatever structure they're in, right? I am kind of visualizing them as little teeny places out in space, right? That have values like 1 or 342 or whatever. And so then my function multiplied by 2 rolls across this, and point by point multiplies them by 2. So the point of point free is you can actually just define the function as not x times 2, but just times 2, right? So you don't need the point. You just have the field, actually. So you're taking whatever space you have and rolling a field through it rather than a point-by-point operation.
There's an implicit variable in point free, is what it is, right? I think is
exactly.
How I understood it.
Yes. You can eta reduction allows you to unexplicate a parameter because it just doesn't affect anything.
Right.
So yeah. Sorry about leaving that one out.
Yeah.
So I guess we could do, I don't know, some more combinators. So the ID combinator, we can say, okay, lambda a dot a, that's the identity. So let's take lambda a dot a on something. No matter what we put in here, we're going to get it out, what we put in out, right? Let's see, right? C34, okay. So that's the identity combinator. Constant combinator might be something like, okay, let's say that 1 equals lambda f fx or something like that, right? Okay, what did I do?
Don't you have to put a parentheses in between those?
Between what? Oh, I need to put like this guy.
Yeah, that's it. Sorry, colon equals is what you needed to use.
Fx. Is that gonna be right? Nope. Okay. Gosh, how do I get?
Hold on. Expression contains free variables. Okay, so do 1 colon equals like you had before. Do lambda x dot lambda f dot fx.
Like that?
Yes.
Right?
That's right.
Okay, so now I just have some value, right? So I can just say 1, right? So now I am using things that are not anonymous, right? I now have a symbol 1 that is no longer, I don't have to go all the way down and construct it out of lambda f dot lambda x dot fx, right? So 2, I have not yet explicitly applied, named. Oh, what? Oh, it's just a variable, but it doesn't evaluate it, right? Okay, fine. So if I want to say 2, it's going to be what? What will it be? Lambda fx, I believe. Is that right?
2 should be lambda ffx.
Or is it over here? Okay. I don't know. Let's go look it up. If everyone's just wants to hang out in their campfire, let's go look it up.
Right.
Church encoding, right? Church. Let's go to church. It's Sunday.
Yeah, just go to the Wikipedia page. I think it's fairly... For church numerals. Doesn't matter, I think. Yep, there it is.
Okay. Yeah, so 0 has f applied 0 times over here, right? So there's x all by its lonesome. So 0 has 0 times, and 1 equals once, and 2 equals twice, and 3 equals thrice, etc. Right? So any number n, there's an isomorphism between the integer and some number of iterations. That number of iterations of some process, right? Yeah. So church numeral 3 represents the action of applying any given function 3 times to some variable, right? Cool. All right. So we could. So 0 is this. x on x, right?
Right, and it makes sense because since we're dealing with the application of f on x, just having a lambda f dot the identity, which is lambda x dot x, means that we're not applying anything. We're just returning whatever we got, which is equivalent to just zero
Yeah. So the
encoding.
cool thing is, then we can use, if we want to add numbers, we just we can apply a function increment some number of times.
Right.
We don't have to say this many times. We just say this number, right?
Right.
And it automatically iterates it that many times. Okay, so that equals what? Lambda fx dot x, right? That's what we decided?
Yes, that's correct.
Fx.
But please use lowercase letters. Thank you.
Okay.
I'm sorry.
All right, so now I can make a combinator that's lambda a dot 0, right?
Hit enter.
Right.
Yay!
So if I say, what do I want to say? I'll just say f1 using a large number, large letters. F1. Okay, fine. I'll try it. F1 equals lambda a dot 0. So this is my, I'll call it my Z combinator. Well, let's call it that. Okay? So this should always return 0, right?
Right.
So if I call ZC on B, 0. Yeah, church numeral 0. Right, so anything I pass in here so now we have a constant combinator, right? So that's how we can define constants. But this could be, the thing that is constant could be any definition I want, right? It could be some function definition or something like that. But probably that's how the large letter labels here are getting done. But I don't know. I didn't build this. Anyone else want to try something out?
No, I don't think we're getting any questions from the stream either. So
Okay.
I think this is a good place to stop. Thanks everyone for joining, and thank you, Judd, for actually presenting this excellent introduction to Lambda calculus. I sure hope folks enjoyed this presentation. Please like the video so that we can update whatever algorithms that will actually get people to start enjoying our content. If folks who are watching the stream, if you want other topics to be created and talks as part of our Haskell presentations, please let me know and we'll put it on the docket. It might take some time because we are going to be covering for the next couple of weeks until we're actually done with our overview of Haskell, just in general, just going through the Haskell programming language itself. So it might be some time before some of those topics get added, but we'll certainly add them when we can do so. In the meantime, for folks who are going to be joining us weekly, there is a suggestion that in terms of supplementary material that I noticed, Judd, you didn't have this note on, but I'll mention it here. A lot of our study groups are going to be based off of a book called Haskell Programming from First Principles. It's a book that is available for purchase on Amazon, as well as I think there's a what's the name of their website again? I'm forgetting their website again.
Haskell Book.
Haskellbook.com. Yes, you can also purchase it from Haskellbook.com. This is a great book that we'll be using as a basis for our discussions, but we're not going to straight up do a lot of the exercises. But it's a great book to have and do supplementary material on. There are great exercises on there too that will allow you to learn Haskell on a much deeper level. And we're going to be covering some of these topics also. Oh, And according to one of our audience members, Haskell programming also is available in hardcover too as well. So you can actually order it.
Yeah, I think they just did that. Yeah.
All right. So, is there anything else that you want to add, Judd?
No.
Okay, cool.
I'm good. Thanks for everyone for attending. And yeah, I'll try to complete what I promised to do.
We'll see you guys.